Hi, I'm Jang from KAIST Korea. This is a collaborative work with Dongyoung Choi, Donggun Kim, Woohyun Kang, and Minhej Kim. In this video, we will present Splat-based 3D scene reconstruction with extreme motion blur. Let me explain the motivation behind our work. The video demonstrates an example of RGBD scanning speed. The capture has to be performed slowly to avoid motion blur, which makes the process very time-consuming. In contrast, we aim to achieve 3D reconstruction even when the input video contains significant motion blur. In the field of RGBD 3D reconstruction, many previous works have achieved remarkable progress, but most of them were not designed to handle motion blur. Over the past few years, NeRF and 3DGS-based studies have been proposed to reconstruct sharp scenes from blurry images. However, these methods rely on initial camera poses and a point cloud generated by CallMap, which is quite fragile to motion blur. When the input video contains significant motion blur, CallMap often fails and produces incorrect camera poses because it relies on matching visual features in the images. Then how about ICP? When a depth camera moves quickly, the captured depth maps become sparser, but they remain accurate because the exposure time of the TOF camera is short. However, a pair of point clouds with planar or repeated structure can easily fall into incorrect matching. To address this issue, we use a two-step approach. First, for each neighboring camera views, we estimate the optical flow between them and use it to obtain a good initial transform for ICP. Next, we run ICP on top of the computed initial transform. For more details, please refer to our paper. This is a composite point cloud obtained by aligning all depth maps captured in the video. Although ICP worked well for each pair of neighboring camera views, they were not aligned well globally due to drift error. Therefore, we refined the transform matrices and the composite point cloud globally by optimizing 3D Gaussians initialized with them. At this stage, the images are blurry, so the only reliable information is depth. Here we apply a simple trick. We optimize the 3D Gaussians for position and opacity while keeping the scale fixed, and we ignore color and other attributes. When we render color from the globally refined result, it looks messy since we did not take color into account. However, when we render depth, it looks much more refined, guided by the accurate depth estimates. Our method produces a dense and accurate point cloud, whereas other methods either fail or result in inaccurate point clouds. After obtaining the globally refined camera poses and point cloud, we can perform deblurring in the same way as related works. Please refer to our paper for more details. Our method achieved the best and second best accuracy in camera pose estimation, and using these estimated poses, we obtain the best deblurring accuracy. This video shows a qualitative comparison on synthetic scenes. We paused at several frames to highlight the blurriness of the input images. Our method shows the best deblurring results. To evaluate performance, we rendered blurry and sharp videos using Blender. Next, we show a qualitative comparison on real scenes. Again, our method shows the best deblurring results thanks to its ability to obtain a dense and accurate point cloud along with accurate camera poses. Thank you for watching this video.